A turbofan or fanjet is a type of air-breathing jet engine that is widely used in aircraft propulsion. The word turbofan is a combination of references to the preceding generation engine technology of the turbojet and the additional fan stage. It consists of a gas turbine engine which achieves mechanical energy from combustion, 1, and a ducted fan that uses the mechanical energy from the gas turbine to force air rearwards. Thus, whereas all the air taken in by a turbojet passes through the combustion chamber and turbines, in a turbofan some of that air bypasses these components. A turbofan thus can be thought of as a turbojet being used to drive a ducted fan, with both of these contributing to the thrust. The ratio of the mass flow of air bypassing the engine core to the mass flow of air passing through the core is referred to as the bypass ratio. The engine produces thrust through a combination of these two portions working together. Engines that use more jet thrust relative to fan thrust are known as low bypass turbofans. Conversely, those that have considerably more fan thrust than jet thrust are known as high bypass. Most commercial aviation jet engines in use are of the high bypass type, 2, 3, and most modern fighter engines are low bypass, 4, 5. Afterburners are used on low bypass turbofan engines with bypass and core mixing before the afterburner. Modern turbofans have either a large single-stage fan or a smaller fan with several stages. An early configuration combined a low-pressure turbine and fan in a single rear-mounted unit. The turbofan was invented to improve the fuel consumption of the turbojet. It achieves this by pushing more air, thus increasing the mass and lowering the speed of the propelling jet compared to that of the turbojet. This is done mechanically by adding a ducted fan rather than using viscous forces. 6. A vacuum ejector is used in conjunction with the fan as first envisaged by inventor Frank Whittle. 7. Whittle envisioned flight speeds of 500 miles per hour in his March 1936 UK patent 471,368, Improvements Relating to the Propulsion of Aircraft, in which he describes the principles behind the turbofan, 8, although not called as such at that time. While the turbojet uses the gas from its thermodynamic cycle as its propelling jet, for aircraft speeds below 500 miles per hour there are two penalties to this design which are addressed by the turbofan. Firstly, energy is wasted as the propelling jet is going much faster rearwards than the aircraft is going forwards, leaving a very fast wake. This wake contains kinetic energy that reflects the fuel used to produce it, rather than the fuel used to move the aircraft forwards. A turbofan harvests that wasted velocity and uses it to power a ducted fan that blows air in bypass channels around the rest of the turbine. This reduces the speed of the propelling jet while pushing more air, and thus more mass. The other penalty is that combustion is less efficient at lower speeds. Any action to reduce the fuel consumption of the engine by increasing its pressure ratio or turbine temperature to achieve better combustion causes a corresponding increase in pressure and temperature in the exhaust duct, which in turn cause a higher gas speed from the propelling nozzle, and higher key in wasted fuel. Although the engine would use less fuel to produce a pound of thrust, more fuel is wasted in the faster propelling jet. In other words, the independence of thermal and propulsive efficiencies, as exists with the piston engine-propeller combination which preceded the turbojet, is lost. 9. In contrast, Roth, 10, considers regaining this independence the single most important feature of the turbofan, which allows specific thrust to be chosen independently of the gas generator cycle. The working substance of the thermodynamic cycle is the only mass accelerated to produce thrust in a turbojet, which is a serious limitation, high fuel consumption, for aircraft speeds below supersonic. For subsonic flight speeds, the speed of the propelling jet has to be reduced because there is a price to be paid in producing the thrust. The energy required to accelerate the gas inside the engine, increase in kinetic energy, is expended in two ways: by producing a change in momentum, i.e. a force, and a wake, which is an unavoidable consequence of producing thrust by an air-breathing engine, 11, or propeller. The wake velocity, and fuel burned to produce it, can be reduced and the required thrust still maintained by increasing the mass accelerated. A turbofan does this by transferring energy available inside the engine, from the gas generator, to a ducted fan which produces a second, additional mass of accelerated air. The transfer of energy from the core to bypass air results in lower pressure and temperature gas entering the core nozzle, lower exhaust velocity, and fan-produced temperature and pressure entering the fan nozzle. The amount of energy transferred depends on how much pressure rise the fan is designed to produce, fan pressure ratio. The best energy exchange, lowest fuel consumption, between the two flows, and how the jet velocities compare, depends on how efficiently the transfer takes place, which depends on the losses in the fan turbine and fan. 12. The fan flow has lower exhaust velocity, giving much more thrust per unit energy, lower specific thrust. Both airstreams contribute to the gross thrust of the engine. The additional air for the bypass stream increases the ram drag in the air intake stream tube, but there is still a significant increase in net thrust. The overall effective exhaust velocity of the two exhaust jets can be made closer to a normal subsonic aircraft's flight speed and gets closer to the ideal cruise efficiency. A turbofan accelerates a larger mass of air more slowly, compared to a turbojet which accelerates a smaller amount more quickly, which is a less efficient way to generate the same thrust. See the efficiency section below. The ratio of the mass flow of air bypassing the engine core compared to the mass flow of air passing through the core is referred to as the bypass ratio. Engines with more jet thrust relative to fan thrust are known as low bypass turbofans. Those that have considerably more fan thrust than jet thrust are known as high bypass. Most commercial aviation jet engines in use are high bypass, 2, 3, and most modern fighter engines are low bypass, 4, 5. Afterburners are used on low bypass turbofans on combat aircraft. The bypass ratio, BPR, of a turbofan engine is the ratio between the mass flow rate of the bypass stream to the mass flow rate entering the core, 13. A bypass ratio of 6, for example, means that 6 times more air passes through the bypass duct than the amount that passes through the combustion chamber. Turbofan engines are usually described in terms of BPR, which together with overall pressure ratio, turbine inlet temperature and fan pressure ratio are important design parameters. In addition, BPR is quoted for turboprop and unducted fan installations because their high propulsive efficiency gives them the overall efficiency characteristics of very high bypass turbofans. This allows them to be shown together with turbofans on plots which show trends of reducing specific fuel consumption, SFC, with increasing BPR, 14. BPR can also be quoted for lift fan installations where the fan airflow is remote from the engine and doesn't flow past the engine core. Considering a constant core, i.e. fixed pressure ratio and turbine inlet temperature, core and bypass jet velocities equal in a particular flight condition, i.e. Mach number and altitude, the fuel consumption per pound of thrust, SFC, decreases with increase in BPR. At the same time, gross and net thrusts increase, but by different amounts. 15. There is considerable potential for reducing fuel consumption for the same core cycle by increasing BPR. This is achieved because of the reduction in pounds of thrust per pound, sec of airflow, specific thrust, and the resultant reduction in lost kinetic energy in the jets, increase in propulsive efficiency. 16. If all the gas power from a gas turbine is converted to kinetic energy in a propelling nozzle, the aircraft is best suited to high supersonic speeds. If it is all transferred to a separate big mass of air with low kinetic energy, the aircraft is best suited to zero speed, hovering. For speeds in between, the gas power is shared between a separate airstream and the gas turbine's own nozzle flow in a proportion which gives the aircraft performance required. The trade-off between mass flow and velocity is also seen with propellers and helicopter rotors by comparing disk loading and power loading, 17. For example, the same helicopter weight can be supported by a high-power engine and small-diameter rotor or, for less fuel, a lower-power engine and bigger rotor with lower velocity through the rotor. Bypass usually refers to transferring gas power from a gas turbine to a bypass stream of air to reduce fuel consumption and jet noise. Alternatively, there may be a requirement for an after-burning engine where the sole requirement for bypass is to provide cooling air. This sets the lower limit for BPR, and these engines have been called leaky or continuous bleed turbojets. 18. General Electric YJ101 BPR 0.25 and low BPR turbojets. 19. Pratt & Whitney PW1120. Low BPR 0.2 has also been used to provide surge margin as well as afterburner cooling for the Pratt & Whitney J58. 20. Efficiency. Edit. Propulsive efficiency comparison for various gas turbine engine configurations. Propeller engines are most efficient for low speeds, turbojet engines for high speeds, and turbofan engines between the two. Turbofans are the most efficient engines in the range of speeds from about 500 to 1000 km per hour, 270 to 540 knots, 310 to 620 miles per hour, the speed at which most commercial aircraft operate. 21. 22. In a turbojet, zero bypass, engine, the high temperature and high pressure exhaust gas is accelerated when it undergoes expansion through a propelling nozzle and produces all the thrust. The compressor absorbs the mechanical power produced by the turbine. In a bypass design, extra turbines drive a ducted fan that accelerates air rearward from the front of the engine. In a high bypass design, the ducted fan and nozzle produce most of the thrust. Turbofans are closely related to turboprops in principle because both transfer some of the gas turbine's gas power, using extra machinery, to a bypass stream, leaving less for the hot nozzle to convert to kinetic energy. Turbofans represent an intermediate stage between turbojets, which derive all their thrust from exhaust gases, and turboprops, which derive minimal thrust from exhaust gases, typically 10% or less. 23. Extracting shaft power and transferring it to a bypass stream introduces extra losses which are more than made up by the improved propulsive efficiency. The turboprop at its best flight speed gives significant fuel savings over a turbojet, even though an extra turbine, a gearbox and a propeller are added to the turbojet's low-loss propelling nozzle. 24. The turbofan has additional losses from its greater number of compressor stages, blades, fan and bypass duct. Clarification needed. Fluid, or propulsive, efficiency can be defined as A to F equals 21 plus VJVA.